We're going to start a new chapter today and we're going to do some lab test revision. Does that sound okay? Yeah? We're about one lecture ahead of the schedule. Okay? So, chapter 4, double integration. This is quite an important topic for this course, and the way that I'm going to explain it is through just regular integrals that you see from high school, okay? It's the simplest thing. So, let's go back, way back to high school. Okay, oh, you come back. All right, a super common problem from integral calculus in high school. You got a curve, you got 2 points on the x-axis, and you want to calculate the area between the x-axis and the curve, right? So a and b are just numbers. Let's say the function is above the x-axis, so it's positive. We're interested in the area, okay? This is just the super basic entry-level idea for Riemann integrals, yeah? Okay, so this is the expression. Now, when we're integrating there, we're finding the area, but what are we actually integrating over? We're integrating with respect to x. But what region are we actually integrating over? Can anyone tell me?
A to B?
Mm-hmm. Yep. So we're integrating from the point A to the point B, exactly. And that's an interval. So how many dimensions is it?
One dimension?
Yeah, it's not a trick question. So when we do an integral like this, we're computing area, great. But we are integrating over that one-dimensional set. Okay? And so a normal question here is, well, can I integrate over other things? Well, what have we seen this week? We've seen line integrals. We're integrating over a one-dimensional thing. It's just not a straight bit necessarily, okay? What about higher dimensions, like 2 dimensions or 3 dimensions? Is integration even possible? Yes, it is, okay? So again, like we're doing with the area, let me set this up using volume, okay? You could also set it up using area, but I'll just do it using volume. Okay, so let's say I've got some sort of surface. Okay, now the way I've drawn that, you can project that surface onto a rectangle in the xy plane. So let me draw in a couple of extra things. Okay, a little bit rough, but you get the idea. This surface, or part of a surface, is now sitting above, let's say, a rectangle. And the rectangle is in the xy plane. Okay? So instead of this being the interval of interest, now you've got a two-dimensional thing. Okay? So, when we think about area and volume, with integrals, we can actually do both. Okay? We just need to think about what an integral would mean for this more general higher dimensional case. Okay? So let me show you a picture and I'll see what I can do. Okay, all right. Here's a surface. And so from a geometrical point of view, we might want to know what the volume is between the xy plane and part of the surface. Okay, just like we did over there. So what can we do? Well, you can take a bunch of these planes and smash them into the surface. So in the xy plane, that'll form some sort of rectangular base. Okay? So the question is, what is the volume? Above that rectangular base, but below the surface, or that part of the surface. Okay, that's what we're going to look at. Okay, that's sort of some geometric idea. All right, questions so far? Have a look at home. Okay, ooh, 25 people. Questions so far? Has anybody seen anything like this before? We know how to compute area using integrals, but volume? Maybe you've seen, you know, you take a curve and you revolve it and then you integrate. Maybe you've seen something like that. Shells, cylindrical shells, volumes of revolution.
Gabriel's horn.
Yep. So that's you've got a curve and then you rotate it around the x-axis. Yeah, that's in first year, 1131 or 1141. Yeah, it is. I think, or 1231. I think 1131. Okay. So, how do we do it? Well, I am glad you asked. And why would you want to do it? Well, volume's a pretty interesting thing, but we'll be doing all sorts of interesting things with these so-called double integrals. Okay? So in this course, we'll be looking at centre of mass, moments of inertia, and a few other things. Okay, so let me just put that back up there. Yeah, all right. So we have some idea of what we're trying to do, but let's actually look at a case study, okay, a problem. Here we have this expression. I just stands for, I don't know, integral or something. All right? So what does this mean? So firstly, we've got two differentials, dx and dy. Okay? There's two differentials and there's two integral signs. This kind of implies that we're integrating in two dimensions, not one, like that interval from the very, very first example. Okay? So what does this actually mean? Well, when I look at these problems, I usually just break it up into bits. Okay? So forget about the outside integral signs and whatnot, just look at the inside integral. This basically says I want to integrate this function from y equals 2 to y equals 3. Okay? So I'm basically integrating along the y-axis there. Okay? And then once I get an answer in the inside integral, it'll be a function of x. Then I move to the outside integral and I integrate from x equals 1 to x equals 3. My answer will be a number. Okay? So let me show you how we actually evaluate something like this. So I always do the inside integral first. Okay? Yep. All right. So I'm going to keep that outside integral and I'm going to integrate that bit. All right, so when I'm integrating here, I am what are you doing? Is it oh, you're doing it. Okay, that's fine. So you can tell me, integrating y squared, x squared with respect to y, what would we do? We'd imagine x is a constant and integrate with respect to y. So what do we get? Just integrating x squared with respect to y. X squared y, yeah, it's not a difficult thing. Okay, so an antiderivative, that will become x squared y because I'm integrating with respect to y. Okay. All right, what about this one? It'll be negative xy squared. Again, imagine x is a constant and integrate with respect to y. And then finally over here, integrate 2y cubed with respect to y. It's going to be y to the fourth. You divide by the new power, so it's going to be y to the fourth over 2. Now, because it's a definite integral, I still have to work through my limits of integration. Okay, so it's a little bit messy, but we're going to put in y equals 3 first and then take away y equals 2 when you do the substitutions and you'll get a function of x. Okay, so let's continue that. So it's going to be 3x squared minus 9x. Okay, 3 to the 4, 81. Minus, and then you plug in y equals 2. Okay, 2x squared minus 4x plus 16 on 2. All right, so it's a bit of a mess, but you can simplify this and then just, it's a regular integral that you know from school. Okay? Okay, so you know how to do that. Integrate each term, sub in x equals 3, sub in x equals 1, and you'll get something like that. Okay, so the answer is a number. You can relate it to volume if the surface is above the xy plane. And it's a pretty easy thing to do. If you can integrate and you can manage the different y's and x's, it's not a hard thing to do. Okay? Just usually start with the inside integral and then work your way out. Now, what happens if you change things a little bit here? Well, I'm glad you asked. Does. So let me give you another picture here. Where did you go? Okay. Now, the volume of something's always fixed, yeah? So a good question here is, does the order of integration matter if you've got like a rectangular base? So if I integrate with respect to x first and then y, or y then x, do you think it matters for a problem like that? The volume doesn't change, right? So in these simple cases, the order of integration doesn't matter. Okay, so, oh, welcome. So for a simple example like this one, you could also have it as this. Okay? So it doesn't really matter. When you get a bit more difficult, the order will matter a lot. Okay, I think that's maybe what you were talking about before. But for simple rectangular bases, the order doesn't matter. Okay? All right. How are we going at home? Any action? Oh, come on. 25 people. All right, questions. That's the very basic entry-level double integral. We call it a double integral because it's got two integral signs. We're integrating in 2 dimensions.
So our first integral gave us the area, like as if we like put a shadow down onto the xy plane, and then we found the area of another plane, just multiplied it like a, no.
No, not really. No, not really. So basically what we're doing is, okay, let me give you another idea here. This here and this here, they're kind of representing the area of the base, right? And this thing here is the height of the surface. So for three-dimensional things, what's the basic thing you learn in high school? It's like, oh, the volume's the area of the base times the height, right? As long as you sort of got the continuity through it, right? It's the same thing. It just the height, the top of this moves a bit. It's not uniform. Yeah.
So we found an equation for each point of the height.
Yeah, that's what Z represents, right? Yeah. Other questions? Okay. So that's the basic double integral. We're not sure what to do with it yet, but we can use it to look at volumes. And here's the bigger picture. Someone came up to me at the end of the last lecture and said, oh, I didn't understand a thing. Can you just explain everything in a minute? I don't know how to respond to something like that. No, I can't. I've failed as a teacher. And I'm like, what is it that you don't understand? Oh, the bigger picture. And I'm like, it's right there. Anyway, from a computational point of view, here's what's important. The inside integral was usually done first, and then you move to the outside integral. The shape of the base is important. Okay, rectangles or squares are the most simple, nice, friendly kind of base that you could think about. Okay? In many cases, it's a good idea to sketch or draw a picture. So let's do a couple more and see what happens. I'm just going to see if I've got another picture here. No, I don't. That's for the next one. Okay. Let's just do one of these. Okay, so just integrate term by term. So let's do the second one. Okay? So here I would integrate with respect to x first, imagining y is a constant. I'll get something and then I'll integrate again with respect to the other variable. All right, so that's going to become a third x cubed. That's going to become xy squared. Okay, so we sub in and then we'll get an integral involving y. So x equals 0 is just going to give us 0, so. Okay, so nothing fancy. We can integrate that. We know what that is. Okay, so your answer should be a number. Pretty easy. But trust me, things get more complicated quite quickly with this stuff because the geometry changes, the base changes, the function changes. You might even need a change of variables. So we're going to introduce things like polar coordinates, right? Different kinds of coordinate system to make these integrals easier if they're really hard. Okay? Questions? Yes, hang on. I'm waiting to fall down that step, by the way. Someone did it last week.
So far, all of these are to calculate area, right?
Volume.
Oh, so like it's been multiplied by height already?
Well, the height is the height is the thing that you're like the height of z equals x squared plus y squared above the xy plane is x squared plus y squared. Right? So it's like we've got a height, all we need to do is sort of get the base in order and then we'll just, integrate. Okay?
Yeah, that makes sense.
You with me? Yeah. If you can't visualize things, it makes it much harder. So I try to think about it as volume, and we're just computing some volume.
This is also just a dumb question. But
No.
presumably, if like whatever we're measuring the volume off goes into the
What is this?
goes below, say, the x or y
Mhm.
axis, then we have to make two calculations.
Yeah. Yep. You want to say that again for everyone at home?
If I kind of forgot what I was saying.
So if the surface is below the xy plane.
If the surface goes below the xy plane at a point, we presumably would have to make two calculations for the volume.
Exactly. What is this, by the way? It's like, can't escape. Okay, so this is the entry-level stuff. Let's make it a little bit more difficult, a little bit more interesting. And this is where the geometry comes in, okay? So rectangles are nice, rectangles are friendly. Let's look at this one. This is not a rectangle, okay? Here you've got a set omega, and you've got some sort of function of two variables, and that's your omega, okay? So with these ones, drawing a picture can help you a lot, okay? So what does it mean? It means that it's like part of a disk, and x and y are non-negative, so it'll just be in the positive quadrant, right? Okay, so that's the line x squared plus y squared equals 1. You've got one sort of bounding line there, one bounding line there, and then there's your set. Okay, so if I was to draw a picture, what have we got going on here? Okay, that's the disk, right? But I only want a quarter of that disk. And then if I put the surface in and I smash it, what's the volume under the purple surface but above that crescent down the bottom? It goes like a crescent moon. That's what it looks like anyway. Okay? So you're sort of smashing it like that. You're only interested in this quadrant where everything's positive. What's the volume under the purple surface but above that part of the xy plane? And that part of the xy plane is omega. Okay, so... Well, the constraint is written there. X squared plus y squared is less than or equal to 1. And x is greater than or equal to 0, y is greater than or equal to 0. Yeah, so it's all there. It's all there. You just need to look. Okay? So, how do we do it? Well, one thing I'm going to show you now is to simplify with a function of x. Okay, that boundary curve, the curved part of the circle, you can write it as a function of x. In this case, not always, but in this case you can. Okay, so our integral this time is not over a rectangle, it's over a quarter disk. So what does that look like? Okay, well I'm going to just describe omega a bit more. Okay, so this is really, really important. So if there's only one thing you listen to in this lecture, listen to this next bit. That goes for everyone at home. Okay, should I put a message? Listen up. Y'all. Listen up, y'all. Okay. Who can tell me an inequality that y values? It is time to lock in, exactly. Thank you. So y is less than something and greater than something in this context of that shaded region. Who can tell me? Yes, but that's not that's true. But it's not the answer I'm looking for. It is between 0 and 1, but we can say even more, be a bit more precise. So basically, y is the vertical dimension or vertical direction? Huh? So I'm trying to describe that region, omega, but I want to use not x squared plus y squared less than or equal to 1, whatever. I want to have two inequalities for y and two inequalities for x. So I'll add something to it, okay? Now, why do we use inequalities like that? Because they are going to be the limits of integration in our integral sign. Okay, we need one for each of the variables. So y is definitely between 0 and 1, but it's not the description I'm looking for. Let me draw an extra piece of information in. Boom. Right? In this setup, y is between this curve and that curve. Would you agree? Yes. Yeah. Yep. So let's look at the bits that bound this, right? You want all the y points are below this curve but above this curve. They're in between. Yeah, would you agree? So okay, and what about x? Well, x is fine. X is going to be between two parallel lines. Right? We go from here over to here, but no more. So in this setup, we can write it like this. Okay? Now, you will be expected to take regions like this and describe them using these inequality signs. You can't do the integral without it in most cases. So you need good spatial awareness. Okay? Now there's more than one way to describe this. There's usually two. But, you know, this is fine at the moment. 0 to 1 is correct. Excellent. Everyone at home. All right, so this is sometimes the hardest part of the problem. Just actually describing the domain that you're integrating over. Doing the integration is actually easy, but setting up the integral is harder. Okay? So let's think about it. What does this look like? Well, these are constants, these are not constants. So it makes sense to put these on the outside of the double integral because you want your answer to be a number, right? You want your answer to be a number. So I'm going to set this up like this. The function doesn't change. Okay? So the function doesn't change, it's just that we've put the limits of integration into our double integral. Now it's amazing, students do struggle with this because, you know, maybe they haven't had to describe these kind of regions before, right? But it's a skill that you can learn, and the best way you get good at it is you do lots of problems. Okay? So look for the general trend. You've got two numbers on the outside that are basically parallel lines, and maybe some functions on the inside, right? Oh, so there's a question at home, like why is y below this? Well, that's the function. Y is here in between these two curves. So that's one curve, that's the other curve. Okay? X is up to 1, so we don't want to choose curves for the x because ultimately if there's something involving functions here, your answer is not going to be a number, it's going to be something else. Okay? So let me just draw an extra piece of information in here. If I have, I can do it up here. Okay, if I have that region there, yeah? It's still the intersection of those two regions. So the x is the red, I know it's a bit hard to see, but the red, the strip intersects with part of the disk, and what are you left with? You're left with this bit. Okay? So we're smashing, we're colliding basically two sets into each other, and you're looking for the intersection. Yeah? Okay? Yeah. So let me show that. So there's a couple of good questions here. So the integration of dy is going into the page and dx is the normal. Sort of. I mean, I would just think of it as integrating over the base, really, and you're multiplying by the height. Could you do y between 0 and 1 and that? Yes, you could. You could. So there's at least two ways to make these descriptions. So, you know, instead of having vertical parallel lines, you'd have horizontal parallel lines, right? And then part of that curve. So this comes with practice, and it comes with doing a lot of problems. So doing the actual integration now is not that difficult, right? So you do the inside integral first. You imagine x is a constant, and you integrate. Okay, so that's going to become x squared y squared over 2. That's going to become y to the 4th over 4. And your limits of integration are going to go in a second. Yeah? All right, so when you put those in, you get a little bit of simplification, thank goodness. And that's an integral that you recognise from school, so yes. But that's not the difficult thing. The difficult thing is describing the region in the first place, in the sense that that's where students have problems. Okay, so there's a general rule with setting up these integrals. Two parallel vertical or horizontal lines, and then maybe some other curves in between where the intersection of those sets gives you what you want. Okay? Okay, questions? Questions? So good spatial awareness is pretty important for these kind of problems. And this is only 2D. Suddenly you can do 3D and 4D. You just have more integral signs, right? N dimensions. It's pretty hard to visualize N dimensions, right?
I just have a question about why we did square root 1 minus x squared.
Well, we need to... So would you agree that if I... Like that part of the curve and that equation, they're the same? Because x and y are positive? Yeah? Oh. So, what are the y points between? Hello, welcome. Is everything okay? I can hear you down here. I can hear everything. So, we need some limits of integration for the y's and the x's, yeah? So here's one, right? This is our region. So I don't want to go any lower than that, and I don't want to go any higher than that curve. Because if I go out of those regions, then we're no longer in the quarter disk. Does it make sense? Yeah. Other questions? Yes.
Can you just explain a little more about why x's limits are evaluated at constants?
Well, what happens if they weren't? Right? So it's a good question. So we're looking for a number, basically, here. So we're looking for a number. What happens if these numbers involved x's or y's? Yeah, you don't get a number, that's for sure. Right? So, yeah, we sort of need... I guess what we're doing, we're trying to bring this into a volume context by forcing it to get to output a number, right? So if I showed you that the picture again from GeoGebra, let me just show you that. Wait. Okay. So the question here is the purple thing is the surface. And then you've got that quarter disk down there. So what is the volume above the quarter disk but below the purple surface? Right? Yeah. And think about it, are we integrating over a rectangle here? No. Right? We're not, sort of a quarter disk. So if it was a rectangle, we'd have two parallel verticals and two parallel horizontals that smash into each other. Other questions? Hang on. Yep.
What is the mathematical reason that if we do it in reverse, so we put the variable outside, then it would be like not the same like values? Because I'm trying to do it, but it doesn't. Yeah.
So here's where it gets a bit more complicated, right? If you wanted to reverse the order of integration here, so not dx dy, but not dy dx, but dx dy, you would need to change these representations, right? Suddenly it's not like this. You're moving to this sort of situation. To horizontal. This is like y equals 1, y equals 0, right? And then how far does x vary? Well, this is like... Oh, hang on, let me show everyone at home. Okay, so that's what we had before. Now we've got... So you have to change the descriptions and the limits of integration if you want to change the order in this more complicated case. All right? There was another question. Hang on.
Will we ever get asked a question where the second integral is a function, like the n terms? In that case, do we flip it?
Oh, yeah. So we'll ask you all sorts of different questions with this one, right? But sometimes you need to flip it, sometimes you don't, right? Sometimes there's a simple way of describing the region, sometimes there's a complicated way. You obviously want to choose the simple way. Yeah, let's do another one and see if we can work it out. Okay, so there's the bigger picture, but let's actually look at these integrals. I know you had a question, so don't worry, I haven't forgotten. All right. So, this is -1/4, by the way. I keep finding mistakes. Okay, let's look at the first double integral, part A. Part A. What is the region of integration? That's the first question, okay? Now you can do it, you can just integrate it, right? No problem. But let's, you do that bit first, you got an x in the integral sign, okay, so what? Right? But let's draw a picture of the region of integration. So what's this? Y is between 0 and x is between 0 and 1. Okay, so for part A, y is between 0 and x is between 0 and 1. Okay, what does that look like geometrically? Ooh, it's a triangle, yes. Okay, so where does that come from? So let's draw a picture. The way I usually do it is I draw the boundary, right? So I draw y equals 0, y equals x equals 0, x equals 1. Okay, here's x equals 1, here's x equals 0, here's y equals 1. Okay? So it's a triangle, but there's two triangles in that picture. I'm confused. Is it the top triangle or the bottom triangle? The bottom? Let's see. Okay. X is between 0 and 1, so we're definitely in that strip. Okay. Y is less than or equal to x. So if we go vertically, we don't go above that line, y equals x, and it's bigger than 0. Okay, so where is the intersection? Bump, bump, bump. That is the little rectangular region that this problem wants you to integrate over. Okay, it's a triangular, not rectangular, triangular. Okay? So actually performing the integral isn't hard at all, right? You integrate it with respect to y, and then you integrate it with respect to x, and you get an answer. But the integrals get harder, and the geometry gets harder. Okay? So it's good if you can draw pictures. It's good if you can just slow down and say, oh, okay, I want to go that way, and there's my 2 lines, or there's my 2 lines, or there's a curve. Okay? And people, bro, you've got earplugs in. Have you not? Is this your first time here? I got 2 rules, right? You know, okay, no sleeping, no headphones. Bro, it's almost the end of week 3. I'm going to fight them for my whole life, okay? Till I die. Questions? Questions? Looks easy when I do it, but it gets harder. Yes?
What if it's struggling?
Yeah, well, you've got to... If you're struggling to draw the picture, you just got to Slow down, draw the boundary, right? Draw y equals 0, y equals x equals 0, x equals 1. Draw the edges. Draw the edges. And then say, okay, well, which bit do I want? Yeah?
Earlier you said we need to use polar coordinates. So what do polar coordinates in the 3D form look like? Because we know that we've got the cos and sine for 2D, but what's the extension?
Yeah, so in 2 dimensions, the polar coordinates, we'll see them later, is like, you know, x equals r cosine theta, y equals r sine theta, right? There are a few variations on that. You can have cylindrical coordinates, right, in 3D, so it's like a cylinder. So x equals r cos theta, y equals r sine theta, z equals z, right, so just moving up and down a cylinder. You can have spherical coordinates that have 2 angles and a length. I don't think we'll be moving past anything other than polar coordinates in 2D. Yeah. Yep. So it can get crazy, but in this course it doesn't get super, super crazy. Okay, good question. Let me put this up. So omega is just a boundary. Not really. It's not the edge. It's everything on the edge and inside. Okay, it's a 2-dimensional set. A boundary is just 1-dimensional in this case. But here we're integrating over a 2-dimensional set. So in the picture that I showed you before, this is the set in here. Okay? Hang on. This is the set in here. It's not just the edges, it's all the points inside. So that's why I would say it's like a filled triangle. Okay? All right, let's take a 10-minute break. Come on down if you have questions. Then we will do some exam revision in the next lecture. Okay, people, let's get back to it. Did somebody say test prep? So, I wanted to do one question from the review quiz. Okay? The review quiz. So, the review quiz, as far as I understand it, it's just revision. Okay? So, it's not that important for class test or lab test 1. Not as important as the other 2, okay? The other 2 sets of questions. But I will do those today, okay? All right, so let me share this with everyone at home. Okay, this is an interesting question. We didn't do an example like this in the lectures, but it's pretty interesting, and I thought, well, we could do it today, okay? So let's have a look at the question. You've got some function of 3 variables and, find the minimum. Find the minimum, I think they mean minimum, rate of change of phi at p. Now, this is like a directional derivative problem, which is a generalization of partial derivative. What is missing from that question? The direction. Usually with these questions you've got, here's a surface or a function, find the directional derivative at this point in the direction of this vector. There's no vector here. Okay, so people go this and they go, oh no, what do I do? Okay, let's discuss this in a little bit of detail. I've got a point, which is good. Okay, so let's go back to our definition of the directional derivative. Okay, so that's the notation we use. U is a unit vector in the direction of interest, and we can do it as a dot product. Okay, so it's the gradient of the vector of the scalar field or the function dotted with a unit vector in the direction of interest. Okay, what do we know about dot products? Let's go back to first year. Dot products, we know how to compute them. What else can we say about a dot product? Gives us a number, great, yep. So if I've got two vectors and I take the dot product, is there anything I can say about the angle between them? Similar, right? So we know, so let's take all that information and go, okay, math 1131. We know if you have two vectors, A dot B, remember that? Now, because this directional derivative, the way we're computing it, involves a dot product, we can do the same thing. We can do the same thing. Okay? So you've got two vectors here. We can talk about the cosine of the angle between them. Okay? So what is the length of u hat? It's just 1, right? It's a unit vector, so it's got length 1. And what's the minimum value for cosine? -1. -1. So this bit is just 1. Doesn't matter what the angle is, cosine is always between -1 and +1. So we can go, boom. That is the minimum slope, or the minimum, or the minimum I'm moving it around a bit, sorry. Okay? So if you ever forget this, if you can't, you don't know where to start, where is the u vector? You don't need it for this question. Okay? Just remember, dot product can be written as the product of lengths times the cosine of the angle. Okay? So how do you actually solve this question? I'm glad you asked. Well, you'd calculate the gradient, or grad phi, evaluate it at p, take the length and then put a minus sign there. Okay, so let's do that. Yep, so I'm not going to write out i's, j's and k's. So we go up here. We differentiate that with respect to x, y, and z and write it as a vector. Okay, if you do that, it takes a little bit of time, but that's not the point of this question. That's a bit better. And the third one I've got as this. Okay, so we want that at the point P. The point P is here. So we sub in x equals -2, y equals 0, z equals -2. We'll get a vector. If you do that, okay, you get something like that. Now, you probably won't get something like this in the class test or the lab test, but if you've got to find the length of this, how would you go about it? Well, one quick way is just to pull out, right? A common factor, So if you want to take the length of this vector, it's 4 times the length of the simplified vector, right? So that's a nice time saver. But also remember, Mobius has got your back with simplifications. So, yeah. So that is the length, or the I don't know, magnitude, if you like, of the gradient. We don't want that, we want the negative of it. Okay, so sometimes it's easy to forget that, oh, there's a negative sign there because cos is greater than or equal to -1. So minimum rate of change. Ba-bow. Okay. So there's no, I can't remember the formula for that. I just say, okay, dot product, write it in terms of cosine, simplify it. Questions? Okay, maximum rate of change would be that. Okay, the same argument works. It'll just be, less than, and that'll be a 1, positive 1. So maximum rate of change will be that. All right, let's see what's going on at home. Not a lot. 22 people are hanging on. Questions? Questions?
Could you explain again why we use the definition of dot product rather than just doing 16, 16 minus 4 and then 1?
So your question is about that? Yeah? Well, because it's asking for, we don't use the cos theta because they're asking for the minimum rate of change, the minimum rate of change. Okay? You don't know what theta is because you don't know what u is. You don't know the angle if you don't have the vector. You don't know what it is. Right? So this at best gives you a minimum rate of change. You can get a maximum rate of change. The actual true rate of change is somewhere in the middle. Yeah. Yeah, you don't know what it is because you don't know the direction. The direction's not specified. Yeah. Other questions? Ooh, great question. This is going on the big screen. Enough. You rule. Great question on a Friday afternoon. What happens if the dot product is 0? Okay, so let's go back to our picture, or our working, sorry. Directional derivative, right? What would happen, what could we say about the rate of change if that's 0? Well, what's the usual thing when a derivative is 0? Could be, or something in between. Yeah, I would just say that if the dot product's 0, then the slope of the tangent is horizontal, right? It's just horizontal. So it's not increasing, it's not decreasing. Yeah, so good question. Okay. All right, let's do some, great question. Let's do some quiz revision. Okay, now I have selectively picked out line integrals because I think line integrals are probably the most involved part of lab test 1. Okay, and because there's a lot of things to do. You've got to describe a curve, you've got to differentiate, you've got to do a dot product, then you've got to integrate. Oh my God. Right? So, this is an example, and it looks a little bit different to what I did in lectures. A little bit different. So, I wanted to explain the notation here. Okay, but let's just read the question carefully. You've got this weird dx, dy. What is going on with that? Well, let me put it into some context for you. Okay, so usually what we've seen in lectures is something like this. Why can I never find the right pen? Yeah. Okay, you've got a curve, you've got a vector valued function or a vector field, and you're integrating it like that, right? So the thing that they want us to evaluate doesn't actually look like that top form, or does it? Or does it? So let me show you. If I've got a way of describing the curve that I'm integrating over, here it is. They actually give you the parameterization. Oh my God, aren't they nice? Right? I can form the differentials for this, right? So you can kind of think of it as, I don't know. Okay, so the dashes mean derivative, the dt's are the differentials, right? So how does that work with this kind of problem? So let me have a look. Okay, so dx, I can just replace that. So actually, maybe it's better if I write it like this. Yeah, that's a bit better. So dx comma dy. All right, so what does this look like? Well, x cubed y, 3x minus 3y. And let's push that dx and that dy there. Okay, so it's still a dot product, but if I expand it with this notation, this is better notation, I'll get exactly what they have there. Okay? So think of it as a dot product that you can expand and you've got the same sort of integral. Okay, so how do you actually compute it? How do you compute it? Well, you can do it a number of ways, but the secret is basically here. Okay? If dx is that, if x is that, then dx equals 1 dt. Just differentiate. And if y is that, dy is 3t squared dt. So I'm going to take those expressions and I'm going to put them in for here and here and here and here, right? So x is t, y is that, replace. dx is that, dy is that, replace. Okay? All right. So let's call that I. So we're going to get x cubed, that'll be replace x with t. Okay, y is t cubed, and dx is 1 times dt. Okay, now over here, 3x is going to be 3t, 3y is going to be 3t cubed. And dy is 3t squared dt. And we're integrating from t equals 1 to 0. So now it looks a bit weird because you've got 2 dt's, but you can just factor them out. So I'm going to take that and just move them. So it's just one expression. Ba-ba. So that is an integral that you can do. Okay? So this is what they call a differential form of a line integral. It's still a line integral. It still means that top left-hand corner, they've just used slightly different notation to express it. Okay? So, you just integrate this in the normal way and everybody's happy. You'll get something like that. Okay? Now remember, Mobius is your friend. It can simplify. I can't be bothered simplifying those fractions. Can you? I just put it in. How did I do? How did I do? Okay. Neo wanti ma? Wanti. You can tell me. What's up?
I just didn't fully understand what's the meaning of the RT equal to the XT and the YT.
Oh,
yeah.
So they're just parameterizations, right? So you can think here. Well, you don't need the t there, right? But so maybe it's even better if you can, if you want, just remove the t's for now, right? If you want to. But here, here's your expression. Yep. That's your first function of t, that's your second function of t. Okay? Now, who can tell me, and I'm looking at people at home who are still hanging on, there's 21 people at home, right? If you have a curve, who can describe that curve to me? What is it? What is it? What curve is it? They're algebraically, they're polynomials, yep. What else can we say? But it's in parametric form. But if I just wanted to, if I just wanted to understand what is the actual curve that we're integrating over, how would you describe it? Yeah, it's a cubic, right? It's a cubic. Yep. So how did I get that? Well, just put in x equals t here, you get y equals x cubed. Yeah? So what part are you integrating over? That bit there. Okay. In that direction. So that's your C. Okay? So sometimes, not always, but sometimes you can just bring it back to stuff that you already know. Questions? Okay, a little bit. I actually think that's a pretty accessible question because you're given the parameterization and you just got to do some derivatives and a dot product. Okay? Questions at home. Cubic is correct. Yeah, you guys are still awake. Okay. Yes. All right, so let's do another one. Let me have a look into my bag of tricks here. Oh, yes. Is that it? Oh, yes. All right. So, for everyone at home, This is a really good question. Okay, so I know some people they don't want to speak Australian or read Australian, but it helps, right? It helps if you can read the question carefully. It's a two-part question. A conservative force field or a conservative vector field is given by this expression. The most important word there is conservative, right? So from a vector calculus perspective, what do we know about conservative? That's the most important information. Okay? Well, we don't even need to calculate the curl because we're told that it's conservative. Okay? So, if we can find this function phi such that the gradient of phi is the vector field f, then that saves us a whole bunch of time. Okay? It saves us many minutes of time. Okay? So let's try to do it. Let's try to do it. All right, so let's look at this and then we'll compare it with this. Okay. Two partial differential equations, phi sub x equals 9 sine 3x, phi sub y equals 4y. Now when we integrate we have to be careful because the constant of integration is a bit strange in these situations. Okay? So what can we do? Let's try. So we integrate this with respect to x. So sine's going to become negative cos. And then I'm going to have a so-called constant function of integration, but actually it's a function involving the other variable y. Okay? Let's do the second one, phi sub y equals 4y. So integrate that with respect to y plus some other function that depends on the other variable. So now the challenge on this Friday afternoon is to pick H1 and H2 such that the bottom two expressions are equal. So, what could we choose H1 of y to be? 2y squared. And what about H1 of x? Oh, sorry, H2 of x. Yep. So if you choose that to be that, let's try some colours, and that to be that, you get equality. Okay? So you're just comparing it. Yes? Yeah, but if you differentiate this, if you differentiate that, do you get that? Because the 3 comes to the front? Yeah, it's okay. It's good to ask because I do make mistakes. Don't worry. I make so many mistakes. So assuming we've integrated it correctly, let's just make those choices. So our phi function wow. Okay. So now we've done that, we want to do something with the phi function. It is the fundamental theorem of line integrals. Okay? So. Okay, the fundamental theorem of line integrals. It says that this, you don't even need to calculate it, you just evaluate it at the endpoints of the path or the curve or whatever you're integrating over. Okay, so let's label some stuff. Let's label this as point B and this as point A. Okay? So, oh, not that. Sorry, the gradients disappeared. Okay, yep. So just, sorry, I wrote that, just rub that out. Because the integral and the gradient disappear. Okay? There. All right, so now we just got to plug in our values into phi, and we'll get a number for our answer. Okay, so you plug in x equals pi, y equals 1, I think that's correct. Let me double check that. Yeah, x equals pi, y equals 1, and then x equals 0, y equals 0. Okay, so if you do that, you will get 8. Okay? The second part of the question is a bit conceptual. Okay, it's a bit conceptual. Let's have a look at what it's asking. Part B. Enter the exact value of this line integral in the box below, where C is a closed path. Now, there's something a little bit strange about the integral sign. Okay, what do you notice about the difference between this integral sign and this integral sign? It's got a little circle on it, right? That kind of implies that you're integrating over what's called a closed path. So like a circle, a rubber band, anything that sort of takes you back to where you started. Okay? So in this situation, they're just saying C is any closed path. Okay? And I've put in 0. I've put in 0 here. How do I know it's 0? How do I know it's 0? So again, bit conceptual.
If it's a closed cycle and you return to the beginning, the work done is 0?
Yep. Or algebraically, if you're going around, like you're saying, you're going around something like that, right? And you start here and you end there, so let's say you go that way, who knows? Well, these are the same because you're at the same point. So it's got to be 0 by the fundamental theorem. Okay? So you don't even need to work out anything there. You just know, okay, well, the fundamental theorem applies. The endpoints of the path are the same. The answer's got to be 0. Okay? The hint there is they don't tell you what C is in the question. They just say C is a closed path. You don't know what it is. You don't need to know. Yeah? You don't need to know. Questions?
I still don't understand why C is equal to 0. I don't understand why C is equal to 0.
C is not equal to 0. So we're integrating over the curves, any curve C, Right? C is not 0, but the answer of the value of the integral over any curve C is 0. Okay, so C is not 0, it's the integral that's 0. Okay, so usually, okay, so let me draw another picture. Here's our starting point and here's our end point, right? And the fundamental theorem of line integrals says the integral, the value of the integral is this. Yeah? Now what happens when A and B are the same point? What is this difference? That's it. Okay? So work smarter, not harder.
Can we just also find the curl of f? So because C is just like an arbitrary large curl, then
Yeah, like you could, but why? I mean, you don't need to do any calculations. You could if you want to find the curl of f and say a 0 vector. Yeah, you could do it, but it's not necessary. Not necessary.
When do you know to use the fundamental theorem of line calculus?
There are a few triggers. That's triggering me right now. Okay, that I feel triggered by that use of conservative force fields. Okay, that's basically code for saying the curl's 0, and you can flick the switch on the fundamental theorem of line integrals. Okay.
Yeah, I guess I was just asking more in like general, like is it a certain type of function that you have to look out for?
Look, I think for the purposes of this, you'll probably be told. But even when you're not told, these nice fundamental theorems still may apply. So there's a little bit of experimentation if you want to do it. I don't know of a good test beyond. I have done it in a few of the problems, hasn't worked out. I don't know of another test beyond the curl test, but yeah.
It's like curl equals 0.
Yeah.
Can use it.
Yes, you can. That's your sort of green light to say, hey, I can go out and find and try to calculate this phi.
Okay.
Yeah. Show me. Show me. So it's not going to. So irrotational. Would you say that's an irrotational field? Because if you drop a little paddle wheel in there, is it going to spin? I think it looks like it's going to spin. Yeah, but that's the thing. We don't want rotation. So if the curl's 0, then there's no rotation of those paddle wheels. So yeah. There was another question there.
Just like a lot more on a fundamental level.
Yes.
Is it just something that we consider? So if something is conservative, that means it's irrotational, thus leading to curl equals 0 and so on and so forth?
Yeah.
Right.
Yep. And, you know, I guess another thing here is, like, conservative fields are path independent, right? So here, they don't tell you what the curve is or what the path is that you're integrating over. So, you know, you could make a connection. Conservative fields are, the line integrals, they're independent of the path, right? That's another good one. Okay? Let's see what's happening at home. Okay. Good question. How do you know when to use phi or find R of t? Okay, so if you see the word conservative, if you see the word fundamental theorem, or word fundamental theorem, if the curl's 0 vector, then you can use the fundamental theorem of line integrals. Okay? All right. Okay. Here's one I've created earlier because I know we don't have a lot of time left. This is another variation. So let's go through it because there's something different about this one relative to the previous examples. And the difference is the parameterization. Okay? So you've got a vector field, but then you're told there's a straight line from 212 to 131. Okay, so you've got the direction from A to B. The question is, how do I describe that little line segment, that little curve? So I showed you in lectures last time, you just use the triangle inequality. So, so you go from here to here, and then you go from here to here. Okay? So once you've worked out your parameterization, you want to evaluate your vector field along it. So basically replace, x, y, and z with your t values or t expressions, and then you get some vector field all in terms of t. Okay? So here's your parameterization, here's your derivative, and here is your vector field along our parameterization. Okay, so you can take the dot product of the bottom two and then you integrate it. Okay. Ba-bop. Okay, so this is a little bit more challenging because you are expected to describe the curve. It's not given to you, and I don't think this is a path-independent curl equals 0 thing. Okay, so I don't think you can use the fundamental theorem of line integrals here. I think I tried, it didn't work out. But prove me wrong. Prove me wrong. Okay? Questions? Oh, hello. Are you in the next class? What is it? What is the name of the class? No, it's okay. No, it's not. Just tell me. I'm interested.
No, I'm just like having a look.
You can join us. Yeah, it's engineering maths. Have a seat. Just pretend like you're paying attention, though. Is that okay? All right, cool. Other questions? And no headphones, that's the other thing. Questions? So this question's slightly annoying because you need to do a little bit more work. Okay? No pun intended, right? No pun intended. Okay. How's everyone doing at home? How is everyone doing at home? 20 people. I keep going back to the screen and I'm seeing how many people have dropped off. The weekend has already started for these people. All right, let's wrap things up. Anybody who has questions, come on down. Please don't ask me to summarize the last 2 hours in 30 seconds. But enjoy the weekend. If you're going to the Roundhouse, have a good time. Groove Armada. And I'll see you next week.